Today we will be solving this problem called chessboard and queens. So our task is to place 8 queens on the chessboard so that no queens are attacking each other. As an additional challenge, each square is either free or reserved, and you can only place queens on the free squares. However, the reserved squares do not prevent queens from attacking each other. How many possible ways are there to place the queens? So first of all, this problem is very similar to the 8 queen problems, and the 8 queen problems is a way easier because there is not this additional constraint of having reserved squares. And what they mean by these reserved squares is that you cannot place a queen here. So we have to check for that as well. And besides that, placing queens require that they do not attack each other. That means that they should not be in the same column or the same row or the same diagonal. So these are the conditions we have to check for. So let's write down the conditions we have to check for. So first, there should not be a knot on same row. Two, not on same column. Three, not on same diagonal. And 4, square not reserved. So let's think about the positions that will be given to our queens. So we know that each row will have a queen. So this is fixed. So we know that in row 8 we'll have a queen, but we don't know in which column. So for each row, we do not know the column of the queen. So for example here, this, let me choose another color. For example, in the first row, our queen might be here. So this means that no other queen can be in this column. So, and in the second row, our queen might be here, for example. Let's go ahead and fill all these. I'm doing this pretty randomly. Let's give this, and this. And if you notice, so in the first row, the column, the queen was placed on the 4th column. On the second, it was placed on the 5th. On the third, so this is 6, this is 2, this is 1, this is 8, and this is 7. So the configuration I put the queens in this example gave us this list of columns that each correspond to the accordion row. So the first row got this column and so on. And what you can notice here is that this is a permutation of numbers. So this is a permutation of numbers from 1 to 8. So basically, any possible arrangement of the 8 queens is just a permutation of numbers from 1 to 8. Because no matter where you place your queens, I can just look at their columns, and I'm gonna get something like this, and it's gotta be a permutation of numbers from 1 to 8 because no two queens can be placed on the same column. So each number here will be distinct, and I will have numbers from 1 to 8. So our problem now boils down to just going through all permutations and checking which ones are valid. So this is where we got now. So we need to go through all permutations from 1 to 8 and check which ones are valid. And whenever we encounter a valid arrangement, we just increase our counter. And if we go back here, our queens are by construction not on the same row because each queen is placed on the different row. So this is checked. We don't need to check for this anymore. And this is also checked because the queens are not on the same column, because as we said, our rows are just the array 1 to 8, and our columns is a permutation of 1 to 8. So these numbers are distinct and these numbers are distinct. So we cannot have two queens with the same row or with the same column. So this is checked. All what we have to do now is checking for these two last conditions. And the fourth one is actually the easier to check, because once we say that we're gonna place a queen here, all what we need to do is to check if this square is reserved or not. And to do that, we just look up our array of characters that represent the chessboard, and we check whether this is a point or a dash. And if it is a dash, we just stop right there because we've got our contradiction. So this is easy. So this is our last challenge. So how do we check that two queens are on the same diagonal? And in order to do that, let me just make some more room here. So I need this. I'm gonna erase this. So now checking for diagonals. As we said, let's say that can I erase this too? Yes, that's cool. Okay. So if a queen here, no other queen can be on this diagonal. So it cannot be here, nor here, nor here. You get the point. So if we look at this coordinate right here, it is at point 1, 2. How about this point here? This point is at coordinates 3, 4. And the next one is at coordinates 4, 5. So if you notice here, the difference between the y and x coordinates is precisely 1. And this is an invariant for this diagonal. So for this diagonal, all the if you take the y value minus the x value, you will get 1. For this diagonal, and the y value will be 3 and the x value will be 1, for example. So here you will get 2, here you will get 1, here you will get 0. For this diagonal you will get 3, 4, 5, 6, 7. What about this one? Here you will get negative 1 because for example this cell has coordinate 2, 1. So if you take y minus x, you will get 1 minus 2, which is negative 1, and this is negative 2, and so on. And in order to avoid these negatives, instead of looking at y minus x, we could actually look at something like 7 plus y minus x. This ensures that our values are always positive. So for example, if you take this cell, its y minus x would be 1 minus h, which is minus 7, and with this 7 it would just become 1. It would just become 0. So this formula guarantees that the values are always positive and they go from 0 to 15, and 15 will be obtained at this point, I guess. Here we will have 8 minus 1, which is 7, plus 7, which is 14, so we're just gonna get 14. So from 0 to 14. So to summarize, each diagonal, if two cells belong to the same diagonal and you calculate this value for the two cells, they should give you the same value. So one last example, if we take this cell and this cell, they are on the same diagonal, and this value for this would be 7 plus 2 minus 3, which would give us 6, and for this cell it would be 7 plus 4, what is this, 7 plus 5 minus 6, which would also give us 6. So this is an invariant. But we are not done, because there could be on the other diagonal this one. And this one is actually pretty straightforward. Let's try to come up with the formula for it as well. So let's look at this diagonal. What are the coordinates of these points? They are 1, 4. How about this point? They are 3, 2. This point, 4, 1. So if you notice, on these diagonals going from right to left, we just have to look at x plus y. So for these, we have x plus y is always equal to a constant if the 2 points belong to the same diagonal. So here they are, if we go, so here they are equal to 1, and here they would be equal to 3. Yes. So here we'd have 1 plus 1, which is 2, sorry. This would be equal to 2, these would be equal to 3, these to 4, these to 5, and so on until we get to the last one, which would be equal to 14 or 16. It depends if you count 0 based or 1 based. If we count 0 based, we would get 14. So here we would have 14. Here we would have something like, or in this case, if we add, so this is 16, 15, 15, and these are 14s. So to summarize, we'll just get a permutation for the columns. So we'll go through all permutations of numbers from 1 to 8 to find the y coordinates. So we'll go through all permutations of a number from 1 to 8 to find the y coordinates of our queens. And because we know the x coordinates which go from 1 to 8, we just need to find the y coordinates, and we check that that square is empty, and then we have an array, a boolean array for diagonals, and we go both ways, small diagonals and large diagonals, and each time we check that this queen is the first queen to appear in this diagonal. If it is not the case, then this permutation does not lead to a valid arrangement, so we'll just move to the next permutation. And this is pretty much it. So let's take a look at the code. So this is our code. We'll start by reading our input. So let's call our vector of strings chessboard. So it will have 8 rows, and for each row we just read a string that represents the whole row. Then we declare our variable count that will keep count of the valid arrangement. Then we declare a vector of size 8 that's gonna represent the column of each queen, and we're gonna use this function iota. This function is built-in functions that when given an iterator to the beginning of a vector, an iterator to some other position, and a starting value, it just goes through those values and each time incrementing by 1. So what I mean here is that at column 0 it's gonna put 0, at columns 1 it's gonna put 1, 2, 3, 4, and so on. So it just fills the array with starting from 0 and each time increasing by 1. Then this is our loop that will go through all the permutations of numbers from, in this case, of numbers 0 through 7. Each time it's gonna give us a different permutations. And as we said in that other problem, the array we started with was sorted, so we're sure to go through all possible permutations. Then we define this boolean called valid that will keep track that no restrictions are violated during for this permutation. And what I mean by that is that we're not gonna put a queen in a blocked square, and we're not gonna have 2 queens on the same diagonal. This first loop will allow us to check if a queen is placed on a square that is already used. So our queens, we're gonna have 8 queens, and each one will be placed on the ith row. That's by construction, and its column will just be the column of this actual permutation. So if this is different from point, that means that this square is reserved. Then for this particular permutation, the arrangement is not possible, so valid should be equal to false, and we just break. And then we need to check for diagonals, and in order to do that, we declare this vector, because as we said here, we said that to check for the main diagonals we have to go through numbers from 0 to 14. That's why we declare an array of size 15. So we declare an array of size 15 and we initialize it with false, meaning that this diagonal hasn't been used before. And as we said, we have to do 2 kind of checks. So this first check is for the diagonals going from right to left. I mean these diagonals, these ones, And for these, as we said, we just have to check for x plus y, and that's what we're doing here. So we check we check that diagonal has not been used before, and if it has been used before, we just state that this permutation is not valid, and then we set the actual diagonal as used. We put true here. And then if all this did not raise any violation to the constraints, we reinitialize our array with false, because we have to, in order to check for the other diagonals. And as we said, for the other diagonals, we check with that formula, x plus 7 minus y. And we do the same thing here. We first check that this diagonal has not been used before, and if it has, we just put false there. And then we state that this diagonal has been used, and that's it. And at the end, if valid is still true, it will increment our count, and at the very end we just print our count. So this is all. Let's compile. Let's check. Let's submit. So this works. Thank you for watching. See you in the next video. Bye bye.